Hi, this is going to be a training video about how to use Zen Black for doing confocal imaging. We're going to start off from the point where we have everything already on, but we're just at the login screen and we need to load the confocal software. So in order to do that, what we're going to do is we're going to open the Zen Black program, which I'm highlighting here, not to be confused with the other icon here, which is Zen Blue. Zen Black is what you're going to use for doing all of your confocal imaging. And Zen Blue is going to be sometimes useful for doing just some file processing or doing some standard Y field imaging. But today we're going to be focused on talking about how Zen Black functions. So to load it, just double click it. Oh, and apparently we already had it open. Let's close it. So to load Zen Black, you have to double click it, and we get a little splash screen. And once it loads, it's going to give you a little prompt window, and this prompt window is going to ask if you want to either A, start the system, or B, do image processing. If you were to click image processing, what will happen is that the software will not actually communicate with the hardware, and you'll only be able to do processing of your images. But today we're going to do start system because we actually want to use the equipment and we actually want to acquire images. So just go ahead and click start system. And from this point on, what's going to happen is that the software is going to be checking all the equipment and seeing if it works. This process is going to take maybe about a minute or so. You'll hear a lot of noises and motors turning in the microscope, and that's a normal thing. If there is a problem that occurs in a startup process, you will usually get an error, which will pop up on the bottom left side of the screen here. So if you see this, then you know that something's wrong. But usually it will go through the whole process perfectly fine. Alright, and for the sake of this video, I'm actually probably going to increase the zoom factor just a little bit so everything can be a bit bigger and easier to see. And you can adjust that up here in the upper right corner of the program. So the main focus that I'm going to talk about today, we're going to be looking at two of these tabs. The first being the locate tab and the second being the acquisition tab. The locate tab is what you're going to use primarily for locating your sample, and that involves making sure that you have the proper lens in place, being able to visualize the sample with either fluorescence or bright field light under the oculars so you can find it and then focus on the sample. And that is the general purpose of what the locate tab is going to be used for. The acquisition tab is where you're going to actually configure the software to be able to image your sample. So it makes sense usually to start from the locate tab. So in the locate tab, what we've done is we've created a lot of these little buttons up here, and you can think of these as kind of like radio presets for stations you might have. So if I have some DAPI standing on my sample, if I click on the DAPI button, what it will do is it'll allow me to visualize and see that DAPI signal. So it'll do a multi-step process. By clicking that one button, it'll open the fluorescent shutter and swap to the DAPI filter in one click. So it's pretty convenient to do things here, and I think it's much easier to do. So the options we have a DAPI filter, a GFP filter, a DS Red filter, and a CF Sci-Fi filter, which is your far red fluorophore. There's a bright field option also. This turns on the halogen light source if you want to see that. And there is a DIC option. DIC for the 10, 20, 40, and 63x lenses. The DIC is going to be used for getting more contrast in your bright field image if you would need it. And if you're interested in looking it up, DIC stands for differential imaging contrast. And then we have the all off button, which turns everything off. So every time I click on one of these buttons here, you'll hear that there'll be some changes that'll occur to the optical configuration here. So for one, it opens the shutter, and then it swaps it to the DAPI filter. And at this point, what I should be able to do is should be able just to go over and look at the oculars and see the sample. But today's sample, I don't have DAPI, I have FITSI and TRITSI labeling. So I'm going to go to the microscope now, and I'm going to get our sample into focus. Okay, so now that I have it in focus, some other things I can do, I can click on the objective, and I can change the objective in the software if I wanted to. I can also do this either by manually rotating the turret objective on the microscope, or you'll have a touchscreen that you can do this on as well. But I'm going to go ahead and do that in this software. So I already have the 10x lens in position, and I already put the sample in focus, so I can just go to the 20x and start imaging from there. And every time you change the lens, you should come look at it, and maybe you might have to refocus it, because the par focality is not perfect, but generally speaking, you'll be in the same ballpark in terms of focus. So here we are. So now we have our sample in focus, and I'm going to click the all off button because I don't want to photo bleach the sample any more than I have to. So that's the purpose that the locate window serves, primarily just to find your sample, to visualize it, and to get it in focus. So now we're going to move to the acquisition tab. One thing I want to point out is that when you switch from the locate to the acquisition tab, the light path or the destination of the light coming from the sample is going to change. When I'm in locate, all the light is going to be going to the ocular, so I can see it, on the microscope itself. When I go to acquisition, you'll hear some parts moving, and what that is that the light is being directed towards the scan detector instead on this system. So if I want to see it on the eyepiece now, I can't unless I go back to locate first. So on the acquisition tab, you're going to have a lot of windows, and it looks kind of intimidating at first, but it's not very intimidating. And all these windows kind of do what they say, but you can click on the arrow on the left and kind of expand it and see what options you have for those. And this workspace is kind of configurable as well. As you can see here, we have the laser window open here, the light path window open here, but if you want, you can click and drag these and move them around anywhere you want on the screen. But if you want to put it back, there's this little anchor button or dock button on the top of it, and it'll put it back to where it came from. You can also click and drag groups of these boxes and put them in different spots, which I'm going to do for the sake of this video so you guys will be able to see the sample. So I put everything on the left side here. Also, you notice that a lot of these windows have these little show all checkboxes. So by default, the software is only going to show you what it thinks is absolutely necessary to get your imaging done, and it may hide some details from you, but if you ever want to see more information, just click the show all button and you can see that. Alright, so when we first start imaging, the very first thing that we have to do is be able to set up a light path that allows us to see our sample. So you could do this manually, and it's a pretty complicated process. You have to set the filters right, you have to have the appropriate lasers on to excite your fluorophores, and you also have to have the right main beam splitters active to reflect the laser down into your sample. If any of these are not right, then your imaging is not going to work. So it's kind of a bummer, but one of the cool things about the software is that we've been given this nice kind of automatic feature for configuring light paths, and that's via this smart setup button. So I'm going to do that now. And the basic gist of it is when you click the smart setup button, is you're going to tell the software what kind of fluorophore you have, and then the software is going to suggest for you light paths based on certain conditions to use to image your sample. So like I said earlier, today I have a FITSI labeled sample and a TRITSI labeled sample. So if I want to add those dyes, I just go to the dye configuration box up here and click on the drop down arrow for select dye, and then I can go and I can select either my dice either from the recent list or from the complete list that is here. So we used Fitzy recently, and we also I think we used Tritzy recently, so I'm gonna select them both from here. But if you wanted to, you can just search for any die that you want. So if you have GFP, you can search for GFP. That'll find everything with GFP in it. And yeah, so it's pretty simple to use. This list is not completely. It doesn't have all of the fluorophores that are known, but it has a very good amount, and usually you're able to find the correct fluorophore or something similar to it from your sample. Alright, so we selected the Fitzy and Tritzy, and yeah, you can also change the color of the channel you want by just clicking on the drop down arrow next to the color box here. So what's going to happen now is that with the Fitzy and Tritzy dice, we're going to get multiple proposals for our light paths and how we want to image. And the 3 proposals that we're going to give us are called fastest, best signal, and smartest. So in the fastest proposal, what is going to happen is that we're going to have one track 1 for our imaging, and the one track in this software will represent one pass on the scan. And as you can see here, it's plotting the emission profile for both our Fitzy and our Tritzy, and it's showing these vertical lines here, which are representing our lasers on the visible light spectrum and where they are relative to the emission profiles. But it's also showing this highlighted portion of the emission profile for both of these fluorophores, and that's representing how much of this curve we're able to actually capture and then be able to visualize with the software. So by combining both the Fitzy and Tritzy into one single track, we are limiting ourselves a bit by cutting off the green capture of Fitzy's to make room for the Tritzy emission here. So that's reflective in this little bar graph up here, which shows us that our percent emission signal for the Fitzy is around 60%, which is typically not very good. But you also notice that some of this curve goes over into the spectrum of the Tritzy channel, and that's represented down on this lower part of this graph, where we're going to have a lot of non-specific green signal crosstalk or bleed into our Tritzy, which is generally not good. So this is not a configuration that we use for doing fixed imaging. When you do the fastest proposal, your primary concern in this case is you want a high amount of speed to get quick imaging done. So for today, we're not going to use this, but if you do have an experiment where time is a critical component, then fastest is something you may want to consider. But yeah, so best signal. In best signal, what's going to happen is that it's going to automatically separate each fluorophore or each channel into separate tracks, and by doing so, we're able to get a much more open filter range, so that we can get more light and we'll get much more percent signal. The downside is that since we have 2 tracks, it's scanning twice as much, and our overall speed is half of that of which we'll be getting the fastest. But when we have a sample which is not live and it's fixed, then this is perfectly fine to image with. The other alternative, won't go too deep into it, but the alternative is called the smartest, and smartest is kind of a compromise between both the fastest proposal and the best signal proposal. But for today, we're going to use the best signal. And if I just select the current option up here and click apply, what's going to happen is it's going to just configure that light path and not do anything. If I, however, were to select one of these 4 options out here, either quality, speed, standard, or Wi-Fi-like, what's going to happen is that the software is going to fix some parameters that are selected when you select one of these options, and it's going to try to sort of do a pre-scan for our image and try to determine the best imaging parameters to look at what the software thinks is what we're interested in seeing. So I'm gonna go ahead and do that. Click the standard button and click apply. And assuming I'm in focus, what we're going to see is we're going to see kind of it do a pre-scan for both channels, do a really quick scan, and then it's going to do an actual scan. So here is our TRITC. It's did a quick scan of it, and then it's going to do a quick pass on the FITC. And then it should acquire an image for both the TRITC and FITC. So I think it's a useful feature because it doesn't always get it configured right, but it usually gets you in the ballpark of what your configuration should look like. Now I'm gonna go through and show you how to configure it manually and kind of tweak your image quality a bit. So the image quality is not bad, yeah. So what we're gonna do now is I'm gonna talk about primarily both the acquisition mode window and the channels window. And I'm gonna show you the more detailed version of this by clicking the show all button so you can see these options. Okay. So the first option that we have for our acquisition mode window is that we can actually change the objective. So I can click on the drop down arrow, and if I click on a different objective, it'll physically move the turret and put the other lens into focus. I don't like to do this particularly here because usually when you change lenses you do have to make some slight adjustments to the focus, but there's an option you can do it here. Scan mode. There's two modes you can have it in. There's a frame mode or line mode. So when you're in line mode, what happens is that the actual scan that will actually occur when you actually click on the snap button here is it actually scan just a horizontal line on the sample. You won't be able to get an image, and you can see, we can do it real quick. You'll just get data. You won't get an actual image. So if you actually want to get an image, you actually want to make sure that you're in frame mode for your scan. So we'll go back to frame. And the next option we have is we can select the frame size. So the frame size is going to determine how many pixels are going to be in your image. So right now we have X dimension of 512 pixels and Y dimension of 512 pixels. You have a small representation of what that image is going to look like here in the scan area, and you can change this. So if you don't want it to be square, you can type in a new pixel range, and you can make it 780 by 512, and then the image becomes rectangular instead. You also click on this little XY button here, and it will give you some pre-configured options for your frame size. And you notice that when I'm in the frame size, I'm at a frame size of 512 by 512, but when I go to line, I get a Y dimension of 1. So it's only scanning 1 pixel in the Y dimension. So let's go back to frame. So the way that this microscope works, it's a pixel by pixel based scanner, and I can show you just a moment here. If you were to zoom in on the image, you can actually see each individual pixel that you have here. So what happens is that the laser will actually run across the image, starting at the top, coming back, and just do this iteratively until it's able to acquire the entire image. So by having more pixels in our scan process, we actually lengthen the total scan time, and that's represented here under the speed option here. So scan time for this setting is approximately 2 seconds. But having more pixels also generally means that you're getting a higher quality image. So there's this trade-off here of getting higher resolution or higher image resolution and scan time. The longer you scan it, the more photo bleaching your sample is going to incur. So where do you want to have this is kind of up to you. I generally, as a ballpark, I start off at 1024 by 1024. I think 512 by 512 is a bit of a small image by today's standards, so I usually stick with that, but if you really want to get a really high quality image or get some publication image, you may want to consider going even higher than that, but that'll be up to you. The other option we have is we have line step. So right now we have a line step value of 1, and what that would do is if I have a line step value of 2, it's going to tell the software that we want it to scan every other horizontal line, and by doing that, it's going to half the scan speed. So if I go to a line step of 2, we get half of our total scan speed, but we're ending up scanning half the pixels. Usually I don't do this. I keep it at line step of 1, but if you want to speed up and get quicker imaging, this is one trick that you can do that. You also have an option here called the optimal button, and what the optimal button is going to do is it's going to give you the optimal frame size resolution to match the resolution of the lens which is currently being used. So if you want to do this, you can do this. Click that button, and it's going to suggest that you use a frame size of 2752 by 2752. Now, granted, this is going to be a much longer image, and for the sake of this video, I'm not going to do that. But that's what the optimal button does for you. Okay, so we briefly talked about the scan speed. So the scan speed is just an integer value that you can set here, and the higher you have the scan speed, the quicker the scan time is going to be. The only downside to that is you're going to get a bit more of a noisy picture. And what I mean by that is that you're going to have some signal in your image which is not really going to be true signal, and that poses a problem, because usually you want to have high specificity and high resolution in your image. So having that scan speed go up higher is going to lose your specificity in your image. So you don't want to have it too high, but on the other side, you don't want to have it too low, because you're also going to be photo bleaching your sample more. And you notice that as I increase this, it shows me the scan time, but also shows me what's called the pixel dwell, and that's going to tell me how long the laser is going to scan each pixel. So I like to start off with a scan speed of 7, but like I said before, if you need more specificity and less noise, you may want to decrease the scan speed. Or in another case, if you're trying to do a live experiment and you want higher temporal resolution, then maybe you will have the scan speed higher. So it really kind of depends on what kind of experiment you're trying to do. But we'll leave it at 7. And right now, I'm just going to go over a couple of ways that you can actually scan the image. So I showed you earlier that you can click the snap button and it just takes a single image for you. And there it is. The other ways of scanning it, you have the live or fast scan mode, and you have the continuous scan mode. So the live mode, once you go to this, it will scan over and over and over again until you tell it to stop. This is mainly useful for making immediate changes to the parameters and seeing how that affects the image right away. One difference is that the live scan mode does not respect our scan speed selection that we had to begin with. So when I go live with a scan speed of 7, it doesn't care what I have previously, and it jacks up the scan speed to be much quicker. So the live scan mode is inherently going to be a bit noisier, but if you want to get a very quick image, that's what you would do. Continuous is like live, but continuous actually does respect your scan speed settings, but it will scan over and over again until you tell it to stop. So a couple of the ways that I can change the image. If I go to live, I can actually move my scan area just around a little bit. And what's happening here is it's not actually moving the stage, but it's realigning the scan mirror so that it points the laser at different areas on the sample. So I can have some movement, but it's not very much movement in each direction. And notice that as I do this, I'm actually adjusting the X and Y here. The other thing that you can adjust is you can adjust the rotation of the sample. So you can click on this and you can rotate the sample if you don't like the orientation of it. You can also click here And you can also zero it out, which means it goes back to the home position. And you also have a zoom factor, so you can zoom into the image if you want, or you can zoom out. See if you can zoom out. You can see a much wider area as well. But for now, we're going to just click on the Reset All button and go to the home position. Now, when you don't, if you don't have the Show All button selected, you won't see these options. So, for the acquisition mode, I'll usually recommend to have the Show All selected. Okay, we also have a section here about averaging. We're going to come back to that in a bit. But for now, we're going to go to the Channels window. So earlier in the video, you may have noticed it, but I came here and I turned off the Tritsy track temporarily just because I didn't want to image both the red and green. But if you want to turn on or turn off tracks, you can do that here just by clicking on this check mark. And right now I have the FTSE channel selected, and what it's showing me down here is showing me the settings that I have for the FTSE channel. And if I click on the Tritsy, it shows me the settings for Tritsy. And everything is not interactable right now because I actually unchecked that. If I check it back, then I can actually see the settings. But what we're going to do is we're going to focus on the FTSE for now, and I'm going to go through all these settings and how it affects the image quality that you have. So the first thing we have is we have the laser. It's telling us that we are using the 48 nanometer laser with a laser line attenuator transmission in percent of 2. So essentially what we're doing is we're using 2% of our laser power to excite our sample. So this is an important parameter. If I increase my laser power, I get more signal. The downside is that you're getting more bleaching that occurs. So typically, having this lower is ideal, but you can adjust that here. The other option we have here is called the pinhole setting, and what this does is it will block out out of focus fluorescence, and it will give us better image resolution at our focal plane. And what I mean by resolution is our ability to resolve structures independently of each other. So for instance, you can see inside this sample here that there's some small dimples where there's no fluorescence. If I were to increase the pinhole to be a bit bigger, you will see that my ability to resolve this goes down. So if I were to increase the pinhole, everything starts to get blurrier, the lines get thicker, and your image quality goes down generally. Even though the image will get brighter, your ability to see structures will go down. And that's really the real critical piece of what makes this system a confocal system, is the inclusion of this pinhole. So ideally, you always want to be at the 1 area unit position, and this allows for the best resolution that you're going to get on the system without compromising signal too much. If you go below 1 area unit, then you're not really getting a whole lot more resolution. You're just losing signal. And at this setting, right, 1 area unit, it shows you that that one picture or one image is getting is acquiring an image that's 1.7 microns thick. And this is a function of both the lens we use and the wavelength of the emission of the light coming from the sample. So as I go up into higher magnifications, you'll see that this section size will get smaller and smaller. And right now, we are using the 20x lens. So the next 3 options that I have of tweaking our sample are the gain master, the digital offset, and the digital gain. So the gain master will adjust the sensitivity of the detector to the sample. So this is an option that doesn't really have a negative impact on either photo bleaching the sample or on the resolution of the sample. But if you have it too high, you'll start to get a lot of background signal, and potentially what you're going to have is a lot of your signal just become saturated. This solid block of green is too bright for our current settings for us to be able to see any detail there. So Gain Master is usually the first thing that I would go to adjust when I'm trying to adjust my my signal quality. But yeah, I generally think that you shouldn't really go too high with this. I'd say about 800 is the maximum that you should have. The digital offset here will also allow us to adjust the signal. And what this will do is, if I have it at a negative value, it'll subtract a certain amount of fluorescence or signal from the entire image. This is not always useful. By default, the value is at 0. But if you wanted to use it to get rid of some background fluorescence in your image, you can do that there. Alternatively, if you want to increase the background fluorescence, you can make this a positive value. Though I don't think this is inherently useful, because it will make your background, instead of black, it'll make it green or whatever your color is for your channel. So usually I'll keep this at 0, but if you need to use it, it is an option to use. And the other option we have is the digital gain. The digital gain kind of works in similar manner to the Gain Master in that you increase it, you get a higher amount of signal. If you do it too much, then you'll get a whole bunch of background signal, like here, which is not what you want to see. So I usually keep this at a value at 1 or close to 1. So one of the things that's important to know is how do you know if your settings are good? Well, if you want to, you can click on this little checkbox in your dimension tab here called range indicator, and what this will do is it'll show you pixels in your image which are saturated. So in other words, pixels which are too bright for the current settings. It'll show up in red. You also have pixels that have intensity of 0 will show up in blue, and this should be usually your background. And so it really depends on what you're looking at. Ideally, you don't want your structures of interest or your sample to be red. Where you want to look at it. But a little bit of saturation could be okay. But in this case, I think I'm going to turn down the Gain Master a little bit. So, with that being said, I think we're going to go back and we'll talk about the acquisition mode, or talk about the averaging box in acquisition mode. So, each pixel is giving a intensity range that it can be. So, when the system scans the sample, each pixel will get a number associated with it, which tells you how bright the image is at that point. And that range of brightness is going to be determined by whatever bit depth you have. You have 3 options. With an 8-bit image, your bit depth is going to range from 0 intensity to 255, which is 2 to the 8th power, or in 12-bit it's going to be 0 to 4095, which is 2 to the 12th power, and then I don't know what 2 to 16th power is, but it's some very large number. So by having your bit depth higher, you're getting more information. Having it lower, you get less information. There really is not a downside to this in terms of speed, though if you have a higher bit depth, your image size will be bigger. So that's what bit depth means. And averaging, if you want to do this, you can set the number of averaging. And essentially what this does is if I have an average of 2 or 4, it means that for our one image here, the system is going to scan each pixel twice if I have an average of 2, and it'll get both of those values, and then it'll give me the average of those intensities as my actual value in the final image. So notice that my scan speed at average number of 1 goes to 3.87, and if I have it at 2, it goes to twice that amount. So I'm scanning the image twice essentially, but yeah, we're getting an averaged image now, and this can be useful for getting rid of a particularly noisy picture, right? So if you have a lot of background, which is kind of or a lot of noise, which is kind of transient signal kind of going in and out, as you average it, that will go down, and your true signal will remain bright. And same goes for doing an averaging of 4, 8, 16, so you can do that here. Has sort of the same effect as decreasing the scan speed. If you decrease the scan speed, you actually slow down the collection of light, and you get a more specific image as well. You can change the mode for averaging. You can do it by line or frame. By default, it's by line. So what that means is that it'll scan each line a number of times, and then print that line as it acquires that line onto the screen. So if I have it in frame, what it instead is going to do is it's going to make a pass of the image, and then scan it again, and scan it again, and scan it again. As opposed to before, where it'll scan each line scan each line 4 times and print that line, so that by the time it gets to the end, it's done. So this is not a really good sample to really show that, because it's really highly specific, but you can do that there. You can also change the scan direction. So by default, as the laser goes across the sample, it's only on in one direction. So this is bidirectional scanning, or no, this is unidirectional scanning, where basically it's only on going from left to right, and the laser will then come back across being off, and then traverse again being on. So it essentially travels the entire image 2 times. If you want to, you can go bidirectional, and this should decrease the scan time by about a half, but you may get a kind of a shearing effect which will happen in your image. It'll be much quicker, but as you zoom in, well, I mean, this is pretty good right now, but you may get something of a shearing effect, and you can kind of see that here, where this should be a nice continuous line, but it's kind of a little bit jagged because we're doing that. So usually, this is a time-saving feature. If you want to scan quicker, you can go to bidirectional, and if you have that shearing effect, you can change the correction for the X and Y here as well, if you need to do that. But we're going to stay in unidirectional mode now. And also under averaging, you have the method here. So if you have an average of 2, and you select snap, it's going to get a mean. It's going to get an average image, but you don't have to do that. If you want, you can set to give you a sum image, and what that's going to do is it's going to take the image twice, and you'll get an image pretty much twice as bright. So it could be useful if you have something which has very low signal. You could use that to increase it more, and at this point you'll see that pretty much everything is saturated. So this is not a good sample for doing that with, but you could do it. Alright, so now I'm going to talk about, now let's see if we can go and get our Tritsy image. And we'll use what we learned before to try to get a good image here. So I turned on just the Tritsy only, and I'm going to turn on the range indicator. And I don't like the image quality that much. I think it could be a bit better, but it's a bit saturated. So what I think I'm going to do is I'm going to decrease the gain master just a little bit, and I might just adjust the focus a little bit. I think that's overall pretty good. Turn both on. Go here and click the snap button so I can get a image with both channels, and then we'll get the overlay of both of those images. So a couple of options that I have here, I have some tabs that I can select. The 2D mode shows me just the merged image of all the channels. If I want to see everything individually, I click on the split, and I can see the red channel and the green channel, and that's there. Yes, I'll have the 2.5D option. It's not inherently useful, but you can look at one channel at a time, but it gives you a 3D map, and it shows you the X, Y, and then the Z coordinate is the intensity map of your image. So you can look at it like that if you want. And like I said, it only does one channel at a time, but you select the channel by clicking on the little top button for it there, and you can see each one. So that's 2.5D. Histogram, this is where you want to go if you want to quantify your image a bit. What's being graphed here is it's taking all the pixels, and it's plotting it here on this graph, and the X is intensity, and then the Y is frequency, and all that data is, all this graph is coming from the data in this table below it. So if you ever wanted to ask the question, how many pixels do I have in my channel 2 track 1, which is a red with 0 intensity, the answer is 153,946 pixels. Yeah, this is all the data you have. This is not inherently useful by itself, but on the table here, what it gives you is it gives you the mean intensity for all channels, the standard deviation, the area, and the number of pixels. So if you were to quantify your level of expression for a fluorophore, you can look at it here and with the mean intensity. You can right-click both of these tables and save them, and they will save just as a text file here as well. Unfortunately, you can't save the graph that way. Also, while you're in the histogram mode, you'll get another little window or little tab down at the bottom here called histogram, and this will allow you to draw regions of interest. So you can look at just the values at a small point. Say you want to look at just the mean intensity inside this little cell or this area right here, and it can do that for you. You'll get the average intensity there, and you also get just the histogram, just the table at that area as well. So that's what histogram is for. Localization tab is if you want to actually go and quantify the degree of localization. You can do that here. I'm not going to go into how to actually do a localization experiment today, but just to let you know that this is where you would do it. In line profile, you're able to draw a line across your image like so, and then you're able to plot the intensity across that line. So in the X we have distance, and Y we have intensity, and we have a table for that as well, and you can right click and save that. You also get a profile little window here, and you can change some properties. For instance, you can make your arrow not a line, you can make it a polyline, so you can bend around it like this instead. You can do a Bezier line, and then you can change some of the options down here as well. Unmixing, I'm not really going to go too much in this, but unmixing is where you can do some spectral imaging, and you can teach the software what your fluorophore is. Say, for instance, if you don't know what your fluorophore, how it should emit its range and emission, then you can have it scan across the whole spectrum, and then it will look at the emission and plot that profile for you so you can see it, and then you can save that. So that's an option there. The information tab will just show you basic information about how you acquired your image. It shows you the image size, it shows you the dimensions, it shows you the bit depth of the image, the lens. So pretty much anything that you need to actually be able to replicate the image, you can look at in the information tab. So saving an image is pretty straightforward. All you would do is you would click the file, save as button, and save it to where you want. I would like for you to save on the larger drive. The C drive is very small, the D drive is much bigger, and in the D drive there is a folder called user save here, and you can just make a folder for yourself and save your images here. So the file types that you can save as, there's plenty of file types, but the recommended file types are just going to be CZI or LSM. These are proprietary file types for the Zen software. If you want, you can download a freeware version of Zen onto your desktop in your lab or your office or home, and you can be able to open these files, but you cannot open them if you don't have the proper software to open them. But when you save the CZI or LSM file, the file is going to have a whole bunch of metadata about how the image was taken, which is important to keep. So what I recommend to people is that they always save as a CZI or an LSM, and then if they need to, they can then export their images in a TIFF or a JPEG as well. So one of the features that's quite nice about saving as a CZI or LSM, I'll just put this on the desktop, is that if you were to go and let's say you're starting from scratch and you changed a lot of your settings, nothing really works right, and you're having a bad day or something, you can go and you can just you can reuse an image which you've taken before. So I can go reopen the file, go to my desktop, image 3, and it's here, and I can click the reuse button. And what that's going to do is going to reapply the same settings that I used to acquire this image to my current settings here. So by doing so, you don't have to reconfigure everything from the beginning again, and you actually don't have to do a smart setup from the beginning as well. So it's a very nice and helpful feature, and that's why I encourage everyone to save their files originally as either LSM or CZI. Okay. The other tabs here, display and graphics. Display will allow you to change the display properties of each channel here. So if I wanted to make the red a bit brighter, I can drag the maximum down to be a bit lower, and as you see, the image gets more red. I can also get rid of some of the background by taking this left curve and taking it away. Same thing for the green, you can do that here. So sometimes a useful feature if you want to be able to see your sample and you don't want to use a high amount of laser power, you can adjust the display properties of it here. This is not changing the data of the image, it's just changing how it appears in this viewer here. In graphics, you can also you can do a whole bunch of things here, but you can draw a scale bar here. Click on the scale bar icon and just drag it across. You can configure that, change the settings of how you want it to look. You can draw boxes. Pretty much anything you think of that you can want on your image. You can put text on it. That's where you would do that, in the graphics option. So now what I'm going to talk about briefly is I'm going to talk about some of the special experiments that you can do in this software. There's a Z-Stack checkbox, time series, bleaching, tile scan, positions, and regions. So the Z-Stack is a series of images along the Z-axis. If you want to do a Z-Stack, you just click on the Z-Stack checkbox, and you'll see a new window pop down here. Then you can open this up and you can configure your Z-Stack. Time series allows you to take a series of images over time, primarily for looking at live samples. Bleaching will allow you to do an experiment where you purposely expose an area on your sample to a high amount of laser power to photo bleach it, and then to see in a time series what happens after that photo bleach event. A tile scan will allow you to create a kind of a montage image from many images that you collect. And it can do this because the sample has a motorized stage. Positions will allow you to mark and record certain positions on your sample so that you can image all those positions, and the system will then navigate to each point that you save and then take an image. And regions allows you to select a sub area or a region of interest, and then you can select this to do particular things. You can tell it to bleach here, you can tell it to do analysis here, or you can tell it to only acquire the image there. That's what regions does. So that's a kind of a brief overview of what those do. I don't think I'm going to go too much into detail about how those work, but just know that those options are there, and all these experiment types are combinable as well. So if you want to do a Z-Stack and you also want to do a time series, that's completely possible. Just keep in mind that your file size is going to get really big as you add more components to your experiment. You can, and also once you have this, you'll see that the Start Experiment button will highlight, and then it allows you to do that experiment. Alright, so I think that concludes it for this training. I hope it was helpful. If you need help, you're more than welcome to come ask us for help. Yeah, that's the end of the video.